Hello everyone, and welcome back to another tutorial video for our class. In this video, I'm going to be going over an example problem from section 2.4, which asks you guys to apply Euler's method to approximate the solution of a given initial value problem. So as usual, I like to start off these videos by just reminding you or writing up on the screen the sort of key tool or key definition or concept or whatever it may be that is being relied upon throughout the problem. In this case, of course, it is Euler's method. I'm going to leave this up throughout this video, but let's quickly go over once again what Euler's method says. So Euler's method applies when you're given an IVP. That will stand for initial value problem throughout the rest of this course. You're given an initial value problem. Y prime is equal to some right-hand side that's a function of x and y, f of xy in this case, along, of course, with an initial value, y0 is equal to y of x0. And also, the problem will specify for you a step size, h. Now, once you have all of these, Euler's method boils down to just repeatedly applying the formula y sub n plus 1 is equal to y sub n plus h times f of x sub n comma y sub n. You just do that as many times until you go from the start of the interval to the end of the interval. Now, the number of times you're going to have to do that, of course, is going to depend on the length of the interval that you're approximating on and on how small your step size is. I tried to be pretty careful and only assign on homework 5 problems which have a manageable amount of steps that you'd have to do this for, just assuming that some of you guys may or may not be able to use computers for these things. So I tried to make sure everything is doable by hand. If I screwed up on that, if some of these problems are requiring too many steps or really need a computer, please let me know right away, as that is certainly not intended. Alright, so the problem, or the exercise that I want to go over in this video, is exercise 2.4.1 from the textbook, or a slight variation thereof. This problem asks you, in the first part, to use Euler's method with a step size of 0.25 over the interval that goes from 0 to 1/2 for the initial value problem y prime equals y and y0 is equal to 8. Alright, it then asks for our approximation at the endpoint, or at x is equal to 1/2, of course. Forgot to write that down, I apologize. Alright, this is pretty straightforward. This is a very large step size to be using here, and this will result in only a handful of approximation points being found. But that's not too bad for an example, so let's go over. Alright, so we have, so far, that x0 is equal to 0, y0 is equal to 8, and our f of xy is equal to y. Alright, this is very straightforward then. So now by using the formula, let's see. So just by the formula, we get that y1 is going to be equal to y0 plus h times f of x0 comma y0. Now, on an exam, for example, I would like you to at least once write out the full clean formula as is, and whenever you're invoking the formula as is, do at least mention that you're using this formula. So I want to see it written out like this once, and then if you're in later steps, you can plug in the numbers right away, but do indicate that you're using the formula whenever you are doing so. Alright, so here in this case, y0 is equal to 8, h is equal to 0.25, and f of x naught y naught is just going to be equal to, well, f of xy is equal to y, so f of x naught y naught is equal to just y naught. And so this is equal to 8 plus 0.25 times y naught, we already said, is 8 again. and therefore this is equal to 8 plus, well, a quarter of 8 is 2, and we get 10. All right, we've gotten our first approximation point. This is our y1. Of course, this is our approximation at the value of x being 0.25. What this problem is asking for is our approximation at x is equal to 1/2. So we need to do this once more. So again, by formula, and this is what I mean. We get that, actually, in this case I'm going to rewrite everything. Y2 is going to be equal to y1 plus h times f of x1 comma y1. As you can see, all of our subscripts are incrementing at every step. And this is going to be equal to, well, y1 is 10, h is, as always, a quarter, and f of x1, y1 is just equal to y1 in this case. So this is 10 plus 0.25 times 10. And this gives us y2 to be 10 plus a quarter times 10, which gives us 12.5. And this is our approximation. To y of 1/2. All right, it's really as simple as this. Of course, this problem is a very straightforward one. The derivatives are pretty easy and clean, and the step size that you're asked to use here is pretty large. But really, nothing else is going to change when you work on problems, even ones more complicated than this. It's just the process is going to be completely the same. It's just that the actual things that you're plugging in are going to be a bit more messy and maybe involve a little bit more calculation. With that said, I think it's probably a good idea to go over an example that's maybe a little bit more involved in this, because again, this is basically done. That's really all there was to finding that approximation at x equals 1/2 with the given step size. So what I'm now going to do is I'm going to switch this problem up a little bit to make things a little bit more complicated, but hopefully you'll see that the actual process doesn't change very much at all. All right, here we go. This time I'm going to tackle a variation of exercise 2.4.7 from the textbook. The process again is going to be exactly the same, but in this case I have a slightly smaller step size. Instead of h being 0.25, we're going with h being 0.1. And we have a slightly more complicated derivative that we're working with. Instead of y prime equals y, we have y prime is equal to negative 3x squared y. And of course, our initial value is also slightly different. Again, with all that being said, the process is not going to change at all. There's just going to be some more steps and maybe a little bit more calculation to go through at each step. But nothing other than that is changing. Okay. So what do we have? We have that h is equal to 0.1. We have that x0 is equal to 0, of course. We have that y0 is equal to 3. And we have that f of xy is equal to negative 3x squared times y. All right, now let's once again invoke the formula. And we're going to see that y1 is equal to, of course, y0 plus h times f of x0, y0. Now this means that we have y0 plus h times, now f of x naught y naught, or x0, y0 if you prefer, is equal to negative 3 x0 squared y0. Again, we're just plugging in this formula right up here in for this guy. Very straightforward substitution. Hopefully everybody sees what I've done there. right, now let's plug in all the values. Y0 is 3, H is 0.1, then we have negative 3, X naught is 0, which is being squared, times, once again, 3. Now, of course, when we multiply by 0, we get 0. So this whole thing goes away, which means that this thing goes away as well. And in this case, we're going to get that y1 is going to be equal to 3 plus a big fat 0, which is still 3. Okay. Now keep in mind that this time, we here are approximating y of 0.1 here. So we've still got a little ways to go before we get to our approximation of y at 0.5. All right, I've moved that first step out of the way because we're going to need a little bit of space here. And let's iterate on this. So once again, by formula, we get that y2 is equal to y1 plus h times f of x1 comma y1. So this is equal to y1 plus h times negative 3 x1 squared times y1. All right, our x1 is 0.1. Again, your x's, your xn is equal to, this is actually something that I should point out here, or that I should just add up here. Xn is equal to x naught plus n times h. Cool. So in this case, we've iterated once, so our x1 is equal to 0.1. Okay, plugging everything in, we get that y1 is equal to 3, h is still equal to 0.1, then this here is going to be negative 3 times 0.1 squared times y1, which is still 3. So this is equal to 3 plus 1/10 of negative 9 times 0.01. So this is going to be equal to 3 minus 0.009. And if I did this correctly, this should give us that this is equal to 2.991. And this is our y2. Remember that now x2 is equal to 0.2 because we've iterated this twice. As you can see, these numbers are changing by a relatively small amount every time in this case. That's normal, I believe. On the homework set, it actually tells you that if you need to round, it tells you to round to 3 decimal places. Again, I have not rounded this at all, but this does cut off at 3 decimal places. Just need to reiterate to be very, very careful when rounding before you get to the final answer. This problem is only asking for your approximation at x is equal to 0.5. This is not there yet, so this is still not a step where you should be approximating, even if you, or where you should be rounding rather, even if you could. All right, now at this point we still have to do this, I think, 3 more times. So I'm going to start color coding things just to show you how you can apply this iteratively much more quickly. I'm going to start boxing in 2 different colors the things that you have to substitute. So at this step in the formula here, this 3 and this 3 are now going to be substituted with this value here. And at this very same step, this 0.1 is going to be substituted with this 0.2. So at this point, you can just say iterating. Is going to yield that y3 is equal to 2.991 plus 0.1 times negative 3 times 0.2 squared times 2.991. And just to reiterate what I've just boxed in here, these are the guys I plugged in blue, and this is that guy in yellow. Now, I just plugged this into Google, quite literally, and this gave me a value for y3 of 2.99, or rather, sorry, 2.95518. You can probably get away with rounding this a little bit, but in general, I would advise that you keep one additional digit, at least in the intermediate steps, compared to the number of meaningful digits or significant digits that you're going to have at the very end. So if you were to round this intermediate step, I would suggest that you round it at 4 decimals, not at 3. Of course, at this point, we are going to have x3. It's going to be equal to 0.3. All right, so we're going to have to iterate this guy once more. So once again, now this guy is going to be plugged in here and here. And this guy is going to be plugged in here. All right, I've moved things around a bit to get a little bit more space, but we're just going to keep repeating what we've done. So iterating once more, we're going to get that y4 is going to be equal to, I'm going to do what I preached here and round that y3 to 4 digits. So 2.9551 plus 0.1 times negative 3 times 0.3 this time squared times 2.9551. And just once again, just to be very clear to see where I plugged in what, these are the guys in blue, and this is the guy in yellow. And this is going to give us, I'm going to this time round this. Again, don't use equal signs when you round. And use that y4 is going to be approximately equal to, what does Google say? Google says this is 2.8753. And of course, x to the fourth, or x4, is going to be equal to 0.4 here. Now once again, this guy is going to be plugged in here, and in there. And this guy is going to be plugged in here for our very last step. So iterating one final time, we get that y4, or y5 rather, is going to be equal to 2.8753 plus 0.1 times negative 3 times 0.3 squared times 2.8753. As usual, I'm going to stick to my color coding scheme to make sure that it's very clear what I'm plugging things into. And this is going to give, when I punch this into Google, that y5 is equal to 2.737. Excuse me, this should be an approximately equals 2.737. And there it is. this is going to be our approximation to y of 0.5. So as you can see, there's nothing super complicated going on here. It's just basically very tedious. The longer the interval that you're going to be working over, and the smaller your step size, the more tedious this is. As you can imagine in practice, we basically never do this by hand. Now, of course, on the exam and on the homework set, I assume, I sort of have to go in assuming that some of you guys at least may not necessarily have easy access to computing resources for this kind of thing. So I'm going to make sure that all of the problems on Euler's method on the exam are doable by hand in this way. Now, of course, it will be a little bit tedious, but I will try to make sure that nothing goes any further, at least, than roughly this number of steps that we had to do on this problem. Hopefully I made clear roughly what you can get away with. The rounding, of course, is it's a bit of a game, right? You don't want to round too much in intermediate steps. In fact, if you were using a computer, you would have it try to avoid rounding at all in these intermediate steps because you'd have everything punched into a for loop. But of course, that's not always easy to do when we're doing by hand. So, you can round in intermediate steps. Just try to keep an extra significant digit in all of those intermediate ones so you don't accumulate those rounding errors. Okay, now on the homework set, of course, there's some additional parts to some of these problems. They ask you to compare these values to the ones that you'd get from using the exact solution, because of course, if you look at this problem, this one is separable. We don't need to approximate it. We can get the exact solution. But that's really just to demonstrate the types of errors that you can get in practice when you use Euler's method on any given differential equation problem. Given that that's nothing too complicated, I don't think, I think I'm going to leave it at that for this video. As usual, please let me know if there's anything or if you have any additional questions or any additional issues with these problems, anything else you'd like me to cover, anything that you think I missed from this. I will not necessarily make a tutorial video on the improved Euler's method. I know that I put some problems about that, but the process is basically identical to what I've done in this video, except that the formula is slightly more difficult, or rather slightly more involved, but you're still iterating in the exact same way. So I don't think for now that I'm going to make a video on it, but if people really want me to, just let me know and I might go ahead and do that. Other than that, I anticipate that I will do one other tutorial video covering homework set number 5, so I will see you guys in that one. Alright, bye-bye.